So welcome to another part of the numerical series. So we'll start from Snell's law. So when light travel from one medium to other medium, it either bend towards the normal or bend away from the normal. So this is your angle of incidence, this is your angle of refraction. This you can take n1, n2, these are two medium. So Snell's law says that sin I by sin r equal to n2 by n1. So I is your angle of incidence, r is your angle of refraction. So when r is equal to 90 degree, in that case I is called as your critical angle. Critical angle. In that case you can write down sin I or write down sin C, that is critical angle, that is n2 by n1. So first we'll try to solve this question on the basis of this formula. So the question is given: a monochromatic light travels from medium A to medium B. The angle of incidence is given 30 degree, angle of refraction is given 80 degree. So angle of incidence is given 30 degree, angle of refraction it is given 18 degree. So you have to calculate mu A, that is refractive index in medium A and B, the ratio between mu B and mu A. So if this is A medium, this is B medium, light is traveling from A to B, that means sin I by sin R will be mu B by mu A. So sin I by sin R equal to mu B by mu A. So it will be sin 30 degree divided by sin 18 degree equal to, you have to calculate the ratio mu B by mu A. So it will be sin 30 by sin 30 will be 0.5 by sin 18. So mu B by mu A will be 1.618, or if you round up it will be 1.62. The ratio will be 1.62. Then the next question: a ray of light passes from air which has a refractive index of 1 into a mineral grain of refractive index mu 2, that is 1.62. So here mu 1 is given 1, you can say mu 2 is given 1.62. So you have given angle of incidence, it is 45 degree. We have to calculate the angle of refraction. So we'll put this sin I by sin R equal to mu 2 by mu 1. So mu 1 is 1. So we'll just put sin 45 degree divided by sin R equal to mu 2, because mu 1 is your 1. So sin R will be sin 45 divided by 1.62. So it will be sin 45 so sin R will be 0.436. So R will be sin inverse 0.436. It will be 25.848 or approximately 25.85. So round up into 2 decimal. So answer will be 25.85. So next move to another type of problem, that is your from specific gravity calculation. So the simple formula of specific gravity is your density of mineral or substance, you can say, by density of water. Or you can also calculate by this formula weight of mineral in air. mineral in air weight of mineral in water. So weight of mineral in air and weight of mineral in water. So we'll see. So in this numerical, a rock fragment weighs 48 kg in air. That means weight of mineral in air is 48 kg. When fully immersed in water, the apparent weight reduces to 30 kg. That means the weight in water it is 30 kg. So we have to calculate the specific gravity. The specific gravity will be weight in air by weight in air minus weight in water. So it's 48 divided by 48 minus 30. So 48 divided by 18 it will be 2.66. So approximately 2.67. So the specific gravity doesn't have any unit because it is a dimensionless quantity. So answer will be 2.67. Next, this is similar type of question. So you can pause and try to solve it. So mineral specimen has specific gravity is given here 4.5. Its apparent weight in water. So weight in water it is given 22 kg. So we have to calculate its weight in air. Sorry, it is weight in water. So weight in air we have to calculate. So what the formula says, specific gravity equal to weight in air divided by weight in air minus weight in water. The specific gravity here given 4.5, weight in air we have to calculate divided by weight in air minus 22 will be in kg. So answer will be in kg. So it will be 4.5 minus 22 into 4.5 into weight in air. So 4.5 weight in air minus weight in air equal to 22 into 4.5. So it will be 3.5 weight in air equal to 22 into 4.5. So weight in air will be 22 into 4.5 divided by 3.5. So let's solve this. It will be 28.285 or you can 28.29. This comes to another type of problem, that is your percentage calculation, mole percentage calculation. So these are very common type of question. So you have to calculate the mole percentage of phosphorite. So let's write down the formula. Mg 1.2, Fe 0.8, SiO4. So what is the general formula of olivine? It is R2 SiO4. In R place Mg Fe cation will occupy. That is your octahedral coordination. So during calculation like this, I have to calculate the mole percentage of phosphorite. So here the phosphorite percentage are only affected by Mg. So SiO4 percentage doesn't affect, or SiO4 doesn't affect Mg or Fe percentage. So if you have asked what is the mole percentage of phosphorite, so you just take this divalent site. So this divalent site will occupy whole number of 2. So from which Mg contribute phosphorite and Fe contribute phyllite. So you have asked, the question is asked about mole percentage of phosphorite. So it will be, so mole percentage of phosphorite, it will be 1.2 divided by whole, they will occupy 2 into 100, will be 60%. Next comes to Miller indices problem. So Miller indices is the reciprocal of the Weiss parameter. So here Weiss parameter or Weiss symbol of a crystal is given 3A, 6B, 2C. So to calculate the Miller indices, you have to take the reciprocal, that is 1 by 3, 1 by 6, 1 by 2. Then we'll take the LCM. So here LCM will be 6. So we'll multiply 6. So it will be 3, 1. Sorry, this is 3. 2, 1, 3. It will be 2, 1, 3. So it is asked about the K place. So it is H, K, L. So K place will be 1. Next comes to another type of problem for coordination number. So when these type of questions, you have to remember this radius ratio. So like the coordination number 2, it has a radius ratio less than 0.155. 3, it is in between 0.225 to 0.155. So you have to remember the table. So in question only the radius of cation and anion will be given. So you have to take out the ratio. Then you should remember this table. Then you will able to calculate the your coordination number. So here given radius is given. So you have to determine the coordination number of the cation A. So cation A is given. The radius of cation A is given 0.72 angstrom. Then radius of anion O is given 1.40 angstrom. So coordination number says it is radius of cation divided by radius of anion. So radius of cation given 0.72 divided by 1.40. 0.72 divided by 1.40. So it is 0.514. Now if you remember this table, then you can say what will be the coordination number, because this is not the coordination number, this is the radius ratio. So this radius ratio, it fall within 0.4142 to 0.732. 0.4142 to 0.732, that is your 6. So the coordination number will be 6. So to solve the coordination number problem, this table is very important. So first memorize this table, then take the radius ratio, then you'll know the ratio will fall within this any of these range. So you can choose your coordination number. Then this is also a very common problem. So for this problem, you have to always remember, you have to memorize the general formula of the Mendel group. So here it is asked the general formula. We require the pyroxene. So here it is a pyroxene is given. So the general formula of pyroxene, you can be XYZ2O6. These are octahedral site. This is your tetrahedral site. This is octahedral. This is tetrahedral. Coordination number 6. Coordination number 4. And this is your oxygen side. So always remember the aluminum, it can occupy both tetrahedral and octahedral site, and your calcium, magnesium, they always occupy the octahedral site. So in this question, it is given this formula Mg 1.1, Fe 0.3, Al 0.8, Si 1.606. Okay, so a pyroxene has a chemical composition of this much. So you have to calculate the octahedrally coordinated aluminum. You have to calculate the octahedrally coordinated aluminum. So see, the octahedral position, they add up to 2. Tetrahedral position also added to 2. Now if you rewrite the formula, Ca 0.2, Mg 1.1, Fe 0.3. So it will be 1.1 plus 0.2 plus 0.3 will be 1.6. So they add up to 1.6, they require 0.4 more. So it will be aluminum 0.4. Now this is your XY place. Now it is completely filled. Then we have Z place. So you can write down aluminum 0.4, Si 1.6, then O6. This also 4. Sorry, this also 2. So now the aluminum, that is 0.8, it will be distributed half to the tetrahedral side, half to the octahedral side. So here octahedral coordinated cation will be, aluminum will be 0.4. Also if tetrahedral, if asked about tetrahedral, it will also 0.4. So in this type of question, I have to rely on the general formula. So as this is your octahedral side, so this should add up to 2. So that's how you will know how much octahedral aluminum is required to complete the formula. Next, a crystal phase cuts the crystallography axis as 2a, 3b, infinite c. You have to calculate the Miller indices. So in Miller indices, you just have to take the reciprocal. So 1 by 2, 1 by 3, 1 by infinity. So 1 by 2, 1 by 3, this will be 0, the LCM will be 6. 6 into 1 by 2, 6 into 1 by 3, and it will be 0. It will be 3, 2, 0 or not. It will be 3, 2, not. This is the HKL phase of the Miller indices. Like this is your front bearing and back bearing problem. This is north, south, east, west. So an object is observed at north 30 degree east from point A. So suppose this is our north 30 degree east. This is the point A. So if the positions are interchanged, so if position interchange means this place will come here. Exactly 180 degree, it will revert. So now if the position will interchange, then the bearing will be this one. So you have to calculate from the north. So if this is 30, so this will be 210. It will be 210. So that's how your, if the position is interchanged, that the position is interchanged means the thing will revert to 180 degree. So now that is the A is here, now it is interchanged to this point. So the bearing of this point will be this much, that is your 210 degree. Then come to another question. The competent quartz vein exposed on an outcrop is segmented into 6 rectangular budins of equal size due to extensional deformation. So budin is a, you can say, layered parallel extension. So the long dimension of each budin is 2 cm and the gap between the adjacent budin is 0.40 cm. So the long axis of budins are perfectly aligned. Assume that there is no internal deformation within the budins. Calculate the percentage of elongation. So what is the formula of elongation? That is change in length divided by original length. Original length or initial length. So component quartz vein exposed on a outcrop is segmented into 6 rectangular budins of equal size. So it is divided into 6. So these are 6 budins. So before it was a single piece. Now because of extension they are fragmented. So now each budin is of 2 cm length. It is 2 cm length. Now it has 6 segments, 2, 3, 4, 5, 6. So the original length before deformation, the initial or original length, it will be 6 into 2 cm. It will be 12 cm. The initial length. Now, if it broken into 6 pieces, they will produce 5 gaps. You can see 1, 2, 3, 4, 5. They produce 5 gaps, and the gap between the adjacent budins, it is 0.40 centimeter, which is constant. 0.40. So here remember the length of the gap will be the. So remember the length of the gap will be the change in length. because initially it is a single piece, now it is broken into 6 pieces. Now these gap are the change in length, so it will be 2 centimeter. So you have to calculate the extension, that is change in length. Change in length means 2 centimeter divided by 12. It will be 0.166. Okay. So now it is asked in percentage. So it will be 16.67 percentage. It will be 16.67 percentage. So past this wooden was like this. Okay. This much is your 12 centimeter. Now you understand how the length of the gap will be the change in length, because the length of gap and the total length, they will be add up to 14 centimeter. So final length will be 14 centimeter. Change in length means final length minus initial length. So final length will be 14, then original length 12. If you minus them, there will be 2 centimeter. So that means the length of the gap will be the change in length. Always remember. Next, it is a similar type of problem. So you can pause it and try to solve by yourself. So a feldspar rich layer show 4 woodins form 2 layer parallel extension. So always remember the number of segment, the number of gap will be less than by 1 from the number of segment it will produce. So number of segments is here. So 4 wooden forms. So 4 wooden, each wooden has a length of 1.8 centimeter. So initial length will be 4 into 1.8, that is 7.2 centimeter. Then the separation between the successive wooden 0.3 centimeter, as it is 4 segment. 1, 2, 3, 4 segment means that is 3 number of gap. So each gap is 0.3 centimeter. So length of the gap will be 0.30 into 3, 0.90 centimeter. So now length of the gap or change in length. So elongation percentage, if you calculate, change in length, that is 0.90 divided by 7.2 into 100. So it will be 12.5%. It will be 12.5%. This is also a similar type of question where the calcite vein broken into 7 woodins. 7 woodins each have a dimension of 1.25 centimeter. So initial length or length of the wooden before deformation, it will be 1.25 centimeter into 7, 8.75 centimeter. The length of the gap, so it is broken into 7 pieces. That means there will be 6 number of gap. So 0.20 centimeter into 6 will be 1.2 centimeter. So now elongation change in length, that is length of the gap 1.2 divided by 8.75 into 100. With 13.71%. With 13.71%. So the elongation numericals are very easy numerical. So just have to calculate the initial length, then take the gap as the change in length. Then comes to your reserve calculation. So the formula for ore reserve calculation, that is your volume into specific gravity, and it is always calculated in ton. The unit is ton. Then you can calculate the metal content. Metal content that is your ore reserve into grade, or you can take assay or percentage of metal content. So ore reserve into grade will be your metal content, and ore reserve, that is volume into specific gravity. So let's solve this problem. We have a horizontal cylindrical ore body has diameter of 30 meter. So diameter is given 30 meter. That means radius is your 15 meter. Then length is given 150 meter. The ore has a density. Ore has a density of 3200 kg per meter cube, and contains 4% metal. That means you can take that grade. It is 4%. So grade is 4%. So we have to calculate the metal reserve, means total metal content. So total metal content formula is your ore reserve into grade, or you can say volume into specific gravity into grade. So first we have to calculate the specific gravity of the ore. Specific gravity of ore, that is density is given 3200 kg per meter cube divided by density of the water, that is 1000 kg per meter cube. So it will be 3.2. Weigh 3.2. Why we are calculating specific gravity? You can also solve by taking this density also. So I'll show that, because if you take specific gravity, then answer will be automatically in ton. If you take this density as kg, the answer will be in kg. You have to convert it into ton. So let's first take specific gravity concept. So specific gravity is 3.2. So first, then we have to calculate the volume. So the ore is a cylindrical ore body. So the volume of the cylindrical ore body will be pi r square h. H is your here length. So pi into r square, it is 15 square into 150. It is meter cube. Okay. Then this is our specific gravity, this is our grade. So what will be the metal content? Will be volume, that is pi into 15 square into 150 into 3.2 into 0.04. So answer will be 13,571.6803. So this answer will be automatically in ton. Okay. Because if you take specific gravity, then answer will be automatically calculated in ton. Let me show you how it is coming. So the metal content will be metal content, there is volume into density, can take volume into density into grade. So volume your pi into 15 square into 150, it will be in meter cube, and density is your 3200 kg per meter cube, and metal content will be 0.04. So meter cube will be cancelled. So answer will be in kg. So it will be 13,571.680.3 kg. You know, 1 ton equal to 1000 kg. So if you convert it, the answer will be same. Ton. So if you convert the density into specific gravity, the answer will automatically be in ton. So if you don't convert, then answer will be in kg, then you have to again convert it into ton. So that's why in formula it is always written ore reserve in ton will be volume into specific gravity. Then if you calculate the metal content, it will be into grade or assay value. Understood? So next question, an ore body, a cylindrical geometry, same question, is horizontally disposed with a distance of 25 meter and a length of, diameter of 25 meter and a length of 250 meter. So here diameter is given 25 meter, that means radius will be 12.5 meter and the length of 250 meter. The length is given 250 meter and the density, it is given 3800 kg per meter cube. So specific gravity will be 3.8 and grade is given 6%. So the metal content will be volume into specific gravity into grade. So volume is pi r square is 12.5 into 250 into specific gravity is 3.8 into grade is 0.06. So here we have to calculate in million tons. So it will be 27979.8096 ton. So we have to convert in million ton. So that means 27979.8096 into 10 to the power minus 6 million ton. It will be 0.27 or you can say 0.3 million ton. It will be 0.3 million ton. Next question. A horizontally oriented ore lens can be approximated as a cylindrical having a diameter. Again, diameter is given 8 meter. So we'll take radius as 9 meter. Then length is here given 300 meter. Then density is given 3600 kg per meter cube. So specific gravity will be 3.6 and grade is given or metal content is given 3.5%. So the reserve of the ore body, the metal content or metal reserve, total metal content will be volume into specific gravity into grade. So that is pi into square into 300 into 3.6 into 0.035. It will be 9618.928 ton. So metal content will be 9618.928 ton. Next, in a sedimentary succession, the fast occurrence of fossil species A dated 9 million years is recorded at a depth of 78 meter. So suppose this is species A. This is species A, which has an age of 90 million years, which occur at a depth of 78 meter. At a depth of 78 meter. Then the last occurrence of fossil of species B dated as 45 million years occur at a depth of 18 meter. So another species you will find here B, which is at a depth of 18 meter, which has the age of 45 million years. Okay. Now another species C, which is occur at a depth of 42 million years. So assuming constant rate of sedimentation and no erosion or hiatus within the succession, calculate the average sedimentation rate in meter per million years and estimate the geological age of fossil species C. So you have to calculate the sedimentation rate and you have to calculate the age of the fossil species C. Now see, this species B is at 18 meter, this species A is at 78 meter. So now the gap between these two species, depth gap, it will be 78 minus 18. It will be 60 meter. It will be 60 meter. So from this B point to A point, we have 60 meter length. Now, the age of A, the age of A is 90 millennia and age of B is your 45 millennia. So as it is saying there is no hiatus, no erosion, no unconformity, that means from A to B the deposition is continuous. So that means the age gap between A and B will be the time period that is taken to deposit from A to B. So that is your 45 millennia. That means this 60 meter of deposition occurred in 45 millennia. 45 millennia deposited in 45 millennia take to deposit 60 meter of the thickness of sediments. So in 1 million year it will be 60 by 45. So it will be 1.33 meter per million year. So 1.33 meter deposited in 1 million year. Now the depth of C, it is 42 meter. It is 42 meter. So you can calculate like this: 60 meter deposited in 45 million year. Then 1 meter will deposit 45 by 60. Then 42 meter will deposit in 45 by 60 into 42. That is your 31.5 million years. So the age of C will be 31.5 million year and the rate of sedimentation it is 1.33 meter per million year. So this is a similar type of problem. Try to solve this. We will continue the solution in the next video. So try to solve this and check the next video for the answer. Okay, thank you.